Thank you. So the first thing that I want to do is just provide some details into the tools and concepts that we'll be using in the talk today. And I think that a good starting point for that is to just briefly summarize how a theorist would see a sensing protocol look like. So it's composed of a couple of different steps, the first of which is to just initialize our probe state. And then we allow our probe to interact with a system of interest for a period of time. During these interactions, information regarding the quantity that we're interested in sensing or estimating gets imprinted on our probe. Then after a period of time has elapsed, we perform a measurement on our parameter-dependent probe state, the measurement outcomes of which are also parameter-dependent. And then what we would do is repeat these three steps a large number of times in order to create a data set, which we can then use to construct a statistical model that allows us to construct estimators and see how precise these estimators are. Now, for the specific tools that we'll be using today, we only need to focus on the last two steps of this estimation, the so-called estimation and measurement stages. So we're going to be considering a completely arbitrary quantum probe, and we'll also be considering a specific but arbitrary choice of measurement specified by POVM, and the target quantity that we're interested in sensing or estimated is going to be labeled by omega. So let's suppose that we've done those three steps a large number of times and constructed our data set and created a statistical model. Some fundamental questions that we might be interested in asking or using the statistical model for is to assess how good the quality of the estimate of the quantity, to assess how good the quality of the guess of the parameter that we're interested in sensing is. And also we'd want to know how sensitive our probe and measurement scheme is in general for the specific choice of measurement that we've chosen. So we can actually answer these questions quite straightforwardly using the information that we've gathered. So for the specific true value that the target quantity omega actually has, we can use the measurement outcomes denoted by the label X in order to construct a probability distribution given by this red curve. Oh, that looks nice. Given by this red curve here. And this represents the conditional probability that we've obtained this data set given that the parameter has the true value omega. And then we can ask, okay, suppose we were to change the parameter value by a very tiny infinitesimal amount. If we repeated this process a large number of times again, we can construct a new probability distribution given by this purple curve. And in this particular example, we can see that even though we've only changed the parameter value by a very tiny amount, the probability distributions are quite easy to distinguish from one another. So in this particular example, we would say that our probe and choice of measurement strategy is sensitive to variation in parameters. In contrast to this, if we imagine the same infinitesimal shift in the parameter value and generated this new purple curve, in this case, because the probability distributions are difficult to discriminate from one another, we would say that our choice of probe or measurement is largely insensitive. Now, the mathematical object that quantifies the distinguishability of these probability distributions is called the Fisher information. And this object can be used to quantify the sensitivity of our probe for the specific choice of measurement that we're employing. And as we can see, it's related to the rate of change of this distribution with respect to the quantity of interest. So that's regarding the sensitivity of our setup. We might also be interested in asking how good is the quality of the estimate that we've constructed. So for this, we can consider that the red and purple curves belong to a family of such probability distributions. This is for the same choice of measurement, but this time we're considering different shifts in the parameter values. So what our objective is that we want to discriminate the red curve from all these different delta omega shifts in the parameter value among this family of probability distributions. In this case, it's hard to discriminate the original red curve from these other distributions. So our job is a little bit more difficult. But if we consider the same change in parameter values, but this time the family probability distributions varies a lot, our job is made easier. So based on how distinguishable these family of probability distributions are, there's a fundamental minimum uncertainty in what our guess of the parameter value is, and this is called the Cramér-Rao inequality, which states that the variance in our estimator is lower bounded by the inverse of the distinguishability measure, deficient information, times the number of measurements that we make. And importantly, this is for the specific choice of measurement that we're employing. On a more general basis, of course, we can consider there's an arbitrary number of POVMs that we could employ. And each one of these would generate its own probability distribution, as shown by these different colored curves. And we can imagine that each one of these probability distributions, which corresponds to a specific choice of measurement, has its own family of distributions for small variations of the parameter value, and has its own associated deficient information and Cramér-Rao inequality. So what we would like to do is ask the question, which choice of measurement is the one that generates a probability distribution whose family varies the most significantly for small variations of the parameter value? In the quantum case, we can actually answer this question by maximizing the Cramér-Rao inequality over all possible choices of POVMs. And this leads to what's known as the quantum Fisher information, which is the best possible sensitivity that you can achieve when you're using a given probe and performing optimal measurements. The optimal measurement basis is defined implicitly by this operator, which is called the SLD, symmetric logarithmic derivative. And if you measure in the eigenbasis of this operator, your measurement is going to be optimal. And this is going to be bounded in what's known as the quantum Cramér-Rao inequality, which is a lower bound on the quantum Fisher information. Okay, now in our talk, we're going to be interested not in the single parameter case, but in estimating multiple parameters. In particular, this represents the most general sensing scenario when there are a set of d unknown parameters that we wish to estimate simultaneously. Now, the scalar bound, the quantum Cramér-Rao inequality, gets promoted to a matrix inequality in the multi-parameter case, and this involves the covariance matrix on the left-hand side and the inverse of the quantum Fisher information on the right-hand side. Elements of the quantum Fisher information matrix, which I'll just call QFIM for short from now on, are specified by this expression here, where the QFI for each individual parameter that we're interested in estimating is defined by its own optimal measurement basis. And elements of the quantum Fisher information matrix are given by this expression, which for the two parameter estimation case explicitly takes this form, where the diagonal elements relate to the single parameter precision of the parameter we're interested in, and these relate to variances in the covariance matrix, and the off-diagonal elements encode the correlation between parameters in a statistical sense, and these are related to covariances. The multi-parameter case comes with a number of different subtleties, and one major obstacle in the focus of this work is the invertibility of the quantum Fisher information matrix. So in particular, as we've seen, the quantum Cramér-Rao inequality is a matrix inequality here that involves the inverse of the quantum Fisher information matrix. So strictly speaking, for this bound to be well posed, we require this matrix to be invertible, which means it has to have a finite determinant or non-zero determinant. In a singular case, when the determinant is zero, the Cramér-Rao inequality becomes ill-defined, and it's often said that this is related to the fact that there are certain directions in parameter space which are unidentifiable, and this leads to an infinite variances in those directions of parameter space anyway. Ultimately, though, the subtleties in the multi-parameter case mean that the strategies that are often developed to be optimal in the single parameter case are not necessarily so in the multi-parameter one. And as I said, the kind of question that we're interested in addressing is there still something, a useful way of bounding the precision when we're confronted with singularity, and can we construct estimators for the quantities that we're interested in this scenario? So what I want to do is kind of develop an understanding now of what a multi-parameter estimation problem looks like when we have a singularity. And what I want to do furthermore, what I want to do is to contrast conventional approaches to a singular quantum Fisher information, and contrast it with the methodology that we develop in our work. And I'm actually going to go through a really simple example that's not presented in the article, but I think it's a really pedagogically useful example, which is the Landau-Zener model, which just consists of a single qubit with a magnetic field in the z direction, and a control parameter G, which sets the energy gap between the ground and excited state. And we're going to be interested in making measurements for the ground state. And in particular, we're interested in the ground state sensitivity. And the targets of our estimation are going to be the magnetic field and the control parameter G. So for pure states, the quantum Fisher information is specified by, or is related to the rates of change of the eigenvector, sorry, not of the eigenvector, of the state with respect to the quantity of interest, which in our case is going to be the ground state of the Landau-Zener model. And this expression specifies what the elements of the quantum Fisher information matrix are, which takes this form for the Landau-Zener model. And just as a quick reminder, these diagonal components tell us about the single parameter precision with respect to the magnetic field and control parameter G, and the off-diagonal components encode the correlations in a statistical sense between these parameters. Importantly, the precision bound involves the inverse of the Fisher information matrix, which takes this form for the two-parameter problem. And in the specific case of the Landau-Zener model, surprise, surprise, we find that the determinant is 0, which means that we're confronted with a singular estimation problem. So what are consequences of this? So pragmatically speaking, it means that we can't estimate the magnetic field or the control parameter G simultaneously because the Cramér-Rao bound is undefined. And in particular, what this points to is that the parameters omega and G are statistically dependent on one another. Now, from a physical perspective, how can we interpret this scenario like in a lab or something? So how do these dependencies between the parameters manifest? Well, in a singular case, what we can do is consider different combinations of the parameters, A and B, and A prime and B prime. And in a singular estimation problem, different combinations of the parameters end up giving you indistinguishable signals, which means that if we were just given these two measurement records, we couldn't discern which combination of the parameters A, B, or A prime and B prime generated them. In contrast to this, in a non-singular problem, so this is when the Fisher information matrix is invertible, different combinations of the parameters A, B, A prime, and B prime give you measurement records which are physically distinct, and therefore you can relate them to the appropriate combination of parameters. So in a singular estimation problem, what is typically done? Is there still something useful that one can do? So the typical approach is to use the Moore-Penrose pseudo-inverse. And this is because the Moore-Penrose pseudo-inverse, which I'm just going to call the pseudo-inverse from now on, always exists and is well defined. And when you use the pseudo-inverse approach to bound the estimation of any, both the classical Fisher information matrix and the quantum Fisher information matrix, it's known that this gives you an overly optimistic precision bound on the variance of your parameters. Nevertheless, using the pseudo-inverse approach is quite useful because when we have a singular matrix, it means that the inverse doesn't exist, but taking the pseudo-inverse provides us a means of converting this matrix and bounding the precision in some sense. So the first step that we need to do, for the Landau-Zener model, the pseudo-inverse takes this form, and then the next step is to diagonalize this matrix, which, as we'll see in a second, provides us really useful information. And when you diagonalize this pseudo-inverse, we find that we have 0 eigenvalue. And of course, we expect this because the matrix, after all, is technically non-invertible. So this means that we have at least 0 eigenvalue. And in a statistical sense, this 0 eigenvalue corresponds to the eigenvector where you have information being encoded redundantly in this direction of parameter space. And then we also have one non-zero eigenvalue, and this corresponds to combinations of parameters and the direction of parameter space where information is being encoded non-redundantly. And once we diagonalize this matrix, the Cramér-Rao inequality can then takes this form, where we can see on the right-hand side that we only have one direction in parameter space which is informative, and the remaining directions are uninformative. And when we look at the covariance matrix, we see that it's not a bound on the original set of parameters omega and g, but it's bounded by it's bounding the precision in this transformed basis of omega 1 prime and omega 2 prime. And these represent combinations of the parameters, which in principle should be estimable, but it's not immediately obvious what the correct combination of parameters that you can estimate are. And in particular, in order to get a well-defined bound in this case, one can just project into the estimal subspace. And by defining the precision as 1 over as the inverse of the variance in the subspace where we can extract something, we obtain this optimistic bound on what the precision of the combination of parameters is using the pseudo-inverse approach. But now, while this approach is very useful in providing a bound in the first place, it does suffer from some limitations. One of them is the fact that it doesn't help us to identify which combinations of parameters you actually can estimate. And this is actually really important because ultimately we want to be able to construct an estimator in the first place. That's the whole point of this kind of parameter estimation theory. And the second thing is that it only provides us with an approximate bound and not what the fundamental true bound is. And so what we want to do is use the intuition that, okay, the parameters are statistically dependent on each other. And so what we want to do is try to deduce what the true effective parameter encoding is. And then if we are able to do this, can we combine the knowledge of what the true effective parameter is with the pseudo-inverse approach in order to find what the true precision bound would be. So the reason why I chose the Landau-Zehner model is because in this example, you can actually deduce what the effective parameter encoding is just by looking at the Hamiltonian or ground state. And in general, parameter relationships that lead to singularities, it's not often so easy to discern them as it will be in this case, because they can be dependent on each other in really non-trivial ways, especially in complicated many-body systems and open quantum systems. But anyway, the trick here is to just identify the fact that the magnetic field sets the energy scale. So we can rescale this Hamiltonian by omega, and the Hamiltonian remains unchanged because it only depends on the ratio of G over omega. So what we were able to do, just by looking at the Hamiltonian, is to identify the single effective parameter, the combination of parameter that we can estimate. This is labeled by this big omega here, which is specified by the ratio. And with this information at hand, we can then just compute the single parameter sensitivity for this big omega to obtain what the true bound should be. And when we compare this with the pseudo-inverse approach, we find that indeed this is a less tight bound, and this is more optimistic. So now what we want to do is say, okay, we know what the effective parameter encoding is. How can we promote this? How can we use this information and combine it with the pseudo-inverse approach to rederive what the true bound is? And we'll see why this exercise is useful in a second. And so we use the fact that we know the effective parameter encoding is specified by the ratio, and we combine this with the linearized error propagation formula, which just states that the covariance matrix in the basis of these effective parameters is related to the covariance matrix and the original basis of parameters G and omega, and the Jacobian, where this is the Jacobian of the effective parameter. So we can already see that knowing what the effective parameter is quite important, because this Jacobian is going to be quite different depending on what the functional relationship between your parameters are. Then what we do is we compute the pseudo-inverse again, and we treat the entries of the pseudo-inverse as the entries of the covariance matrix in the original parameter basis. And then we combine it with the Jacobian to write this expression, and we get this form for what the variance of the effective parameter encoding should be. And then when we sub in all the values and calculate this explicitly, we get this guy out here. And we can immediately identify that the inverse of this guy is precisely the single parameter, the effective quantification information of the single parameter, effective single parameter that we were able to deduce just by rescaling the Hamiltonian. So, okay, why was that a useful exercise to do? Well, for the following reasons. So, like I said, in general, we're not going to be able to kind of look at a Hamiltonian or a state and deduce what the effective parameter encoding is. So what we would like is to create a more systematic approach for deducing what these effective parameter encodings are, such that we can use the pseudo-inverse approach to find what the true bound is. Okay, so we do just that in the paper, and we do it for the general case of an arbitrary number of effective parameters. But here I'm just going to give the result for what a single effective parameter would look like. So the first thing that we need to do is diagonalize our Fisher information matrix. In principle, you can always do this because the Fisher information matrix is a real symmetric positive semi-definite matrix. And this matrix D is basically just a diagonal matrix of the eigenvalues of the QFIM. And when we do this, we get only one non-zero eigenvalue, and its corresponding eigenvector tells us about which directions of parameter space information is not being encoded redundantly. And this eigenvector is really important because we can use it in order to discern what the effective parameter is. And we do this by solving the set of partial differential equations that arise from this condition. And in the case of a single effective parameter, you can actually write that in this neat way. And when we solve the set of nonlinear partial differential equations, we get out two solutions, one of which we identify as the correct physical one that we were able to deduce from the Hamiltonian itself. Okay, so although we've kind of introduced this generalized method for deducing what the effective parameter encoding are, which we can then compute with the linearized error propagation formula and pseudo-inverse approach we just discussed, we can already see that in general, this method might not always be super useful. And we can see hints of that even in this really simple example here. So for example, the fact that we have multiple solutions can be a bit problematic because we don't always a priori know which solution is physical. So that can be a bit of a problem. Second of all, solving this set of nonlinear partial differential equations, you can't always do this analytically. So sometimes you're going to have to resort to numerical solvers. And the fact that we have multiple solutions means that we're going to have branch cut issues, which can make our analytics a bit more, we have to be more careful with them, I guess. And what we show in the paper, but not in this talk, is that there's actually some scenarios where the combination, the functional relationship between the parameters can be so complicated that you can't always invert and find the solution to this set of nonlinear partial differential equations. So therefore, we'd like a more systematic and robust way of finding these effective parameter encodings and finding the position. And for that, we turn to the Bayesian approach, which I'm just going to really quickly outline. So the central quantity that we're going to be using is the posterior distribution. And this represents the belief that we have about the set of parameters having observed the measurement data nk. The posterior distribution is composed of the prior, which represents the belief that we have about the parameters before observing any data, and the likelihood, which represents the conditional probability that we've obtained the given data set, given that the parameters have a specific value and some normalization. With the posterior distribution, we can construct estimators in the multi-parameter case by marginalizing over the relevant parameters. And using this, we can also define higher order moments, such as the variance, quite easily in the following way. So what does the Bayesian approach look like in practice compared to 10? Oh, nice. Okay. So what does the Bayesian approach look like in practice? So if we were to look at the posterior distribution for an estimation problem, which is non-singular, so when the Fisher information is invertible, the Bayesian distribution is described by a multinomial distribution, which converges. So let me restart this. So we can see that this converges to a single unique point upon subsequent updates of the Bayesian by using more data, and it eventually converges to a single unique point. And in principle, this is supposed to represent the true parameter values that we want to infer in the first place. Okay, that's cool. But how does this connect to the quantification information approach that we looked at in the first half of the talk? Well, they're connected through the Bernstein-von Mises theorem, which states that in the asymptotic limit of data sets, the Bayesian posterior distribution converges to a multivariate Gaussian distribution, whose covariance is precisely the inverse of the quantification information matrix. Okay, so what happens when the bursting von Misses theorem breaks down? So basically, the BVM is only applicable for invertible quantification information matrices. So when we're confronted with a singularity, what happens to this Bayesian posterior distribution? So for that, we're going to go back to our Landau-Zener model example, and we're going to be, where we've already discerned the fact that the effective parameter encoding is given by the ratio, and we're able to work out what the effective QFI is. And so when we look at the Bayesian multinomial posterior distribution, we see that instead of being described by a multivariate Gaussian, which eventually converges to a single unique point, is described by a line of persistent high likelihood, which never converges to a single point. And this is already quite useful because while traditionally one would say, okay, if your fish information matrix is not invertible, there's kind of like nothing useful you can get. When you look at the Bayesian posterior distribution, you can see that all these black regions represent parameter guesses that we've eliminated, and that we know that the true parameter value lies somewhere along this line. But okay, although the multinomial posterior distribution does not converge to a multivariate Gaussian distribution, what it does converge to is a univariate Gaussian, or at least this is what we showed in our work. And in particular, it converges to a univariate Gaussian whose mean or variance is specified or characterized by the effective parameter encoding. So in principle, whenever you're confronted with a singular estimation problem, if you compute its Bayesian posterior distribution, the functional relationship that you see pops out and would specifically embody whatever complicated function describes the combination of parameters that you can estimate. This is one of the things that we show in our work. And so we can see this here explicitly, that this is given by this ratio line. And so then what this does is it motivates us to do the following. So instead of looking in this kind of line of persistent high likelihood, what we want to do is perform a coordinate transformation into a basis where this doesn't change, and we'll see what that means in a second. So what we're going to do is transform from the original parameter basis of omega and g into these new coordinates, u and v, which is just the standard hyperbolic transformation. And when we do a simple post-processing of this data, we go from this persistent line of high likelihood that's characterized by the functional relationship between the parameters to a line of translation of variance in one direction. And why is this useful? Well, if we take any line cut in the horizontal direction, what we find is that we obtain these univariate Gaussian distributions, and these Gaussian distributions converge to a single unique point when we use more and more data to update our posterior distribution. And then if we compare if we were to compare the variance of this distribution, which is shown in these yellow dots, with the effective QFI that we deduced from the Landau-Zener model, we see a one-to-one matching. So in the Bayesian case, we can readily determine what the effective parameter encoding is. And then by going to a transformed basis where it remains translationally invariant in one direction, you can automatically get what the effective bound on your position is here. Okay, so maybe I went through all that very quickly. But basically, I just want to conclude by summarizing my results. So in this talk, we discussed multi-parameter estimation. And in particular, we were interested in what happens when the fish information matrix from a frequentist perspective has a singular matrix. And we described the general way in which one can find what the effective parameters are by employing the pseudo-inverse approach and diagonalizing the fish information matrix. And then we also saw that the Bayesian approach to parameter estimation provides you with all of this information in a really natural and easy to obtain way. And I also want to thank, before I end, my acknowledgements. So I want to thank Equal1 for sponsoring my PhD, and my two collaborators in China, Abu Faisal and Shobik, and my old supervisors, Andrew and Steve, who I guess their pictures aren't working. Thank you so much. If you have any questions, no.
You said that this pseudo inverse is too optimistic. Can it be like arbitrarily too optimistic, or is there some kind of, it's just a little bit optimistic?
That's a good question. I'm not sure how too optimistic it is. I'm not sure if there's any discussion on how loose it is compared to the true bound, to be honest. But I guess because that's a good question to ask. I guess in principle, people usually just take the pseudo inverse and kind of stop there. And they just look at the optimistic bound. So that's a good question.
I have a different question, but I can ask it here.
You can ask me.
No, it's more involved.
Okay. Yeah.
And so is it true to say that the singularity in the quantum Fisher information matrix comes about somehow because of the overfitting in your model? That's what I got from your Landau-Zener example. Is that the case? You have kind of redundant.
Exactly. So you have an over-parameterized statistical model. But the reasons that can lead to these over-parameterizations are often quite subtle. So for example, in critical systems, you can have situations where as you approach the critical point and observable order parameters are described by universal scaling functions, you can get emergent singularities at critical points that aren't present away from the critical points and this kind of stuff. So it's not always obvious. Like another example that we've looked at in 2 different papers is when you consider the estimation, including this paper, you consider the estimation of a Hamiltonian parameter and something like temperature, which is not a Hamiltonian parameter. And typically you wouldn't expect at all that temperature and the coupling or something would be related in any way. But nevertheless, because of certain symmetries and stuff like that, you can get singularities. Because, so it's kind of interesting the scenarios that can lead to these singularities.
What do you think? If you see a singularity in your quantum Fisher information matrix, that automatically implies that there's overfitting. That's the ultimate always.
That's not always the case. I think that for the type of problems I'm interested in, it will always be the case. But for example, if you're working with an experimentalist sometimes, and they're trying to do multi-parameter estimation, if you don't have sufficient amount of data, you can have a singular matrix. Also, if you can have situations where the particular choice of measurement that you're making will be singular, but if you were to change and use a different choice of measurement, the Fisher matrix associated with that will be non-singular. So sometimes you can have situations where the very measurement that you make is the thing that induces singularity, which is really not trivial. But in general, I think for me anyway, it's because you have this over-parameterization happening. But pragmatically speaking, it's not the only case.
If there's no other questions, let's thank George. Last talk is Alessandro Cramér. No, we have one up here as well.
No, first, do you have a mic? I have here.
Oh.